Hello everyone, in this video we'll discuss about the equivalent single degree of freedom vibration system with rotational coordinates. Now what is an equivalent system, and if we replace an actual system with equivalent system, we mean that the equivalent system should respond to all the forces, to all the movements in the way as the actual system responds. So it is just replacing the members, maybe n number of members with a single member, or maybe by changing the position of the member. But the idea is that whatever is the response of actual system to any force or to any moment or to any agent, external or internal agent, the same should be the response of the equivalent system. Now, let us consider a uniform shaft which is of length L, and it is fixed with the upper end is fixed, and it carries a disc at its other end of moment of inertia I, right? And we are assuming that the mass of the this shaft is negligible, so we will not take it into consideration. Now, what will happen if we are giving a twist to this disc about the vertical axis, and if we release it? So if we try to twist it and if we release it, what will happen? It will start oscillating. It will perform what? The torsional vibration. So if we want to discuss about the torsional vibrations in case of single rotor, so what the equation will look like, or what will be the equation of the natural frequency, that we'll see. So there are certain terms that we need to know. The first is the moment of inertia, we have already discussed. The second term is what? Theta. So theta is what? The angular displacement of the disk from its equilibrium position. So at any instant, if we are displacing, or we are angularly displacing this disk, that is given by angle theta. The next term is Q, which is the torsional stiffness of the shaft, because here the shaft is acting as the restoring element, and it is given by the formula G into J upon I. So wherever we have got the torsional spring or a torsional member, so stiffness is given by G, which is modulus of rigidity. Basically, in case of shafts we are talking, into J, that is the polar moment of inertia of the shaft cross section, and I, which we have already talked, it is the moment of inertia, right? So if we say that the system is in equilibrium, the inertia torque, it should be equal to the restoring torque, right? So what is restoring torque? Restoring torque is basically the stiffness into displacement. So what is displacement? That is theta, and the torsional stiffness is denoted by Q. And what is inertia force? It is basically mass into acceleration, but here, because torsional vibrations are there, or torsional movement is there, it becomes moment of inertia into theta double dot, right? So which is basically showing the angular acceleration. So if we take theta from here to this far side with theta, like if we take I from theta double dot to theta, so this is how the equation looks like. And if we compare this equation, so we find that the natural frequency is equal to under root Q upon I. And if you want to find the frequency, so this is it will be 1 upon 2 pi under root Q upon I. So these two values can be calculated for any torsional system by applying the simple concept that we are assuming that the torques acting on the system, they are zero. That means the system is in equilibrium. You place the values of all the equations, and or place all the values in the equations, and we can find the value of natural frequency, right? So whenever in a system there are multi-masses, and the idea is to replace multi-masses with an equivalent mass, and which is producing the same effect, right? So this example we have already discussed, that if there is a rack and pinion, right, and this pinion is having the angular motion, right? So let's say the angular movement is theta, so angular velocity will be theta dot, right? And what is this transitional mass? So this is the mass that is doing the transitional motion, and the mass moment of inertia for the pinion, let's say, is denoted by J naught, right? So if we want to write the equation and if we say that the total kinetic energy, it is what? The kinetic energy of this translatory, this rack, so it becomes half m x dot square plus half j dot into theta dot square, right? So what exactly we want? Whatever is the total kinetic energy of the system, we want the equivalent kinetic energy with a single mass and with equivalent displacement, right? So we can say that x dot equivalent is equal to x dot if, and theta dot is what? It is x dot upon r, right? So if we write all the values, we can compare m equivalent, so it will be m plus j naught upon r square. So this is how we can write the translational equivalent mass. Now, if we want to write the mass in terms of this rotational equivalent system, so the equation equivalent, that means the equivalent kinetic energy of the system will be half into J equivalent into theta dot square, right? And if we place both these two equations, so what will be x? Now we know that x theta dot is x dot upon r. So x dot will become what? Theta dot into r. So we can replace that x dot square with theta dot into r. So this is how the equation looks like, and we can find J equivalent or the mass moment of inertia for the system, which is J naught plus mr square. Similarly, we can replace multiple springs into a simple or a single spring system. So when the springs they are in series, the deflection is basically so deflection is what? It is the sum of the deflections of all these springs. So the equivalent is given as, so 1 upon Q equivalent will be equal to 1 upon Q1 plus 1 upon Q2 plus Q3 and so on. And in case of parallels, Q equivalent is equal to Q1 plus Q2 plus Q3 and so on. Right? So by using these equations, you can find the spring stiffness, whatever is the number of springs in a system. Right, so here we have taken an example, a simple example to find the equivalent mass of the system. Now here we see in the system there are two springs S1 and S2, and there are two rigid links. So let this be rigid link 1 and let this be rigid link 2, and they are connected to a pulley, right? And the mass moment of inertia of pulley is given, which is Jp, and here we have got a cylinder of mass mc and radius rc, and this cylinder has got no slip condition. So we assume that when the whole system starts moving, there are small displacements in the system. So we can easily find the equivalent mass for the whole system by balancing the kinetic energies of this system, right? So when this mass m, right, if we begin from here, if this mass m is displaced by some value xt, let's assume by some distance, let's say x, so what will happen? The pulley, it will rotate, right? And this pulley will rotate by some angle, let's say theta p. So let's say theta p, and let this theta p be equal to theta 1. So we can write this in terms of displacement, which is x upon, if we say that this distance is, so if this is the radius of this pulley, so this is rp, right? So theta p is what? This angle theta p can be written as x, because this is actually this much displacement will take place if this mass is having displacement x. So same amount with the same curvature, this pulley will rotate. So theta p becomes equal to x upon r p. What will happen? It will cause the rigid link to rotate by one angle. Similarly, if link 1 rotates, link 2 also rotates. When link 2 rotates, what will happen? It will cause the cylinder to roll without slippage, right? So the angle theta c, it is given by what? x2 upon rc. And if the cylinder is rolling, what will happen? Because of the rolling, there will be some displacement in this spring, and the spring will move in this direction, right? So the total kinetic energy of the system, so we'll take all the components, and we are taking into consideration the masses of the rigid links, the pulley and the cylinder. So first component is this mass, right? So this is half mx dot square, plus second component is this pulley. So it will be half jp, which is the mass moment of inertia, into theta dot square, because whatever is displacement, it is taking place in terms of the angle. Now, because of the rotation of this pulley, what will happen? This rigid link is also having some angular motion, right? So it will be half J1 if, let's say, the mass moment of inertia for this rigid link is J1 and its displacement is theta 1 dot square, plus what will happen when this link rotates, this link 1 rotates, this link M2 will have the translational motion, right? Because this is connected to a cylinder which cannot slip, right? So it will be half, if let's say its mass is M2, so it will be M2 x2 dot square, plus again this is a rotational body, so it will be half JC, the mass moment of inertia of this cylinder, let's say be JC, into theta, and whatever angle it will rotate, it will be theta c square, plus half mc into x2 dot square. Now because of the rolling of this mass, now this mass is having this, it is also having this rotational motion, and along with this, because of the spring, it will have the linear movement in this direction. So this is the total kinetic energy of the this cylinder, right? So we can replace the values of theta p, x2, theta c, jc and j1 in this way, right? So basically what we are doing, whatever is the total kinetic energy of the system, we are saying that it is equivalent to some mass with some, let's say, linear velocity x dot square, right? So we can equate all the members of mass. So this is what the equivalent mass that we get for this system, right? And we can find the relationship, like theta p is x upon rp. What will be x2? X2 is this displacement. It will be theta p into L1. That means the linear movement of this link 2 is given by what? The linear movement of this link, because all the other components, they are rotating and this rigid link 2 is fixed at this point, right? So it will be theta p into L1. Similarly, we can find the value of theta c, which is x2 upon rc. Rc is what? Rc is this, right? Similarly, we can find the value of mass moment of inertia of this cylinder, and also the mass moment of inertia of the pulley. Place the values and you'll get the value of the equivalent mass for the whole system.